Hello, everyone. My name is Jack. I'm one of the principal engineers at Mellanox. If you haven't heard of the company, we primarily make networking equipment, and I'm gonna try and explain a little bit about why some of the stuff that we're seeing in networking hardware is intersecting with networking security in kind of an interesting way. Just a few asides at the beginning. So the first one is I know that I'm the gatekeeper to your lunch, being the 11 o'clock talk, so I'll try and be aware of that. The next one is, I apologize for the name. SmartNIC sounds kind of like, smart refrigerator or something like that. This is an industry term. I didn't make it up, but I am reusing it. So apologies if you think smart whatever is a bit played out. Lastly, I never really meant to become a security engineer. I kind of accidented into it. About 2007 or so, I was at a company and we were launching our first software as a service offering. Until then, I'd been shipping on CD-ROMs. And we thought we knew what we were doing, and the service went live. And about midnight that night, they phoned all the engineers because we were under a massive attack already. And that was kind of the introduction to the side effects of building software in a modern way. And since then, I kind of got hooked. Okay, so what we're going to do is I'm going to talk a little bit about some of the trends that we're seeing in a modern data center. And this is both with the way infrastructure is deployed and also the way software is deployed onto that infrastructure. And that'll hopefully outline some of the problems that created the need for something like a more intelligent, more secure infrastructure. Then we'll talk about what a SmartNIC is and kind of the reasons why it's different from a dumb NIC or one that's less positioned to be useful for data center security. We'll look at what a data center looks like if they're deploying something like a networking infrastructure security solution. And then finally, we'll show you some of the cooler things that go beyond networking security to actually talk about how it affects host security, how SmartNICs can do things like just give you a better picture of the world. It's not just a clip on the wire capturing packets. You can actually do some really unique things. So first, it's kind of a problem that you might be aware of if you're one of the people who are in charge of racking and stacking. If you're simply deploying software, you've probably seen this as a more of a side effect for how much software you actually have to deploy. And that's that what we're seeing is that we're no longer deploying appliances in the network. Most of these things are becoming virtualized. So you're not going to see a rack of a bunch of machines with a Tor at the top and then like a ginormous firewall appliance. We're more or less virtualizing all of that, right? So you'll have a virtualized firewall. You'll have a bunch of virtual switches. You'll have, say, like an IPS. What used to be an appliance is now virtualized and living as an agent on the host. And all of this is actually taking up an insane amount of host compute power. So these aren't meant to represent actual numbers, but more the kind of trend that we're seeing. So simply taking the switching problem, just pushing packets between virtual machines, pushing packets between different hosts on a network within a data center, it's consuming so much compute that the more services you deploy and the more hosts you need, the more compute on each host is required for actually moving packets around. And it gets even worse when we start to virtualize the security infrastructure. So where we used to have just appliances that we can throw into the data center, once we virtualize those and put them on the host living alongside each of these services, we see them consume pretty much your entire, like if you have a Xeon farm, it's going to consume most of those cores. So I think, for instance, if you wanted to provide wall-to-wall IPsec between each of your machines in kind of a VPC, you'll consume, I think on a 48-core machine, it's something like 12 cores just to maintain IPsec. So right off the bat, you're just taking a huge hit on your compute power. But in my mind, this is kind of a boring problem. But the real worry is this last bullet point. So most data centers are around 10 gigabit, maybe 25 gigabit. Once you start to get into those kind of bandwidth areas, you consume so much CPU that you have nothing left for security, right? But like I said, this is kind of a boring problem. This is just what caused some of the things that I'm talking about today. So we get into this situation where everything is virtualized, it's getting closer to the data, the network is becoming dumber, and the edges are becoming where everything is done, okay? So let's keep that in mind. Okay, that leads to the attack surface problem. So once we've virtualized literally everything, including the switches, our firewalls, hips, all that kind of stuff, it's now living on the same compute platform, the same trust domain as all of your regular services. So let's say you have a single host, you have some number of virtual machines, you've also got obviously a hypervisor to manage the resources for those virtual machines. Within the hypervisor, you've got some kind of switching framework so that those VMs have access to the network and they can push packets around. The hypervisor, the switching, in this case I used OVS just because it's very commonly deployed, along with all of the policy for that switching framework, they're all stored on the same host, right? And we know VMs can escape their sandbox. We know that there's L1 terminal faults so that we can have VMs inspecting memory from other VMs. We know that there's a whole host of host problems. And now we've got this really sticky problem where as a result of virtualizing literally everything and putting it on the same host, we now find that the attack surface is now shared. So what was once isolated, at least physically, maybe not logically, is now shared both physically and logically, right? The other problem is that things like the hypervisor and certainly services that are connected to the hypervisor, those are all running with escalated privileges, right? So a breach on any of a number of systems that are required just for these applications to exist is going to affect not only the applications, but all of your infrastructure as well. So there have been a number of exploits, for example, where now that this isn't a hardware switch, this is a software switch. This is open to all the same type of software crap that you might expect. Like, forget the advanced stuff like side channel. This is just plain old software, right? I can exploit any number of buffer problems within the switch itself, right? And so we've seen attacks where simply by pushing packets in an intelligent way, I can breach the embedded switch within my hypervisor, and now I have access to the entire host, which includes all of the applications that are on that host. So as a result of the consolidation, we've created this really nasty trust domain. Everything is sort of squished together in a very small way, and this is kind of what we call problem number 2. Okay, the real problem with this is that host security is terrible, right? So if we look at traditional host security, you might think of something like a malware agent or something that's monitoring an application whitelist, or it could even be some kind of IPS system or firewall. The fact that they're all running on the same host is kind of a problem when we look at the total landscape for host-based security. And this is a very small subset. It's just kind of a selective one, just to give you kind of an idea. So we put some of the technological revolutionary items in black and the subsequent exploits in yellow. Finally ending with the L1 terminal faults now, which have reduced the compute problem on the host to an even more severe situation. But the idea is we know that host-based security is maybe not bad, but it's impossible to do what you want to do. If you have two air-gapped systems, that's fantastic. Once you smash them together, they're a little bit worse. And even with things like Stuxnet, that crossed an air gap by design, right? So even in the presence of very sophisticated prevention techniques, we find that host-based security is still incredibly lacking. That's why I absolutely love this quote. I try and use it whenever I can. I'm not going to read it out loud. I'll let you read it. But it kind of summarizes my entire stance on host-based security. Everyone thinks that it's this lockstep thing where you've got a 0 day and then you got a patch, you got a 0 day and you got a patch, and that's how they get in. The answer is no. It's really just time and persistence, right? That was exactly what the opening talk this morning was about. There's no possible way for it to get better, and there's no possible way for you to get ahead of it. The most you can do is try and minimize it and take advantage of the fact that time is the factor. So if you increase time, that gives you more chance to remediate things or inspect vulnerabilities or keep track of your assets. But the only thing that you can't do is shove everything together on the same trust domain, because that'll actually decrease the amount of time that you have. And it'll essentially make it so the persistence and focus that we're talking about here, the thing that'll always get you in, is basically guaranteed to affect everything once it goes down. I love this quote. Okay, so what can we do about this? By the way, is this on? Am I double? Okay, good. Essentially, the real solution here is to create some kind of isolation between security controls and the applications that you're trying to protect. And as a bonus, the security controls, the applications you're trying to protect, and the infrastructure itself. So if you've got something like a sensitive application, and you know that it's going to be targeted, right? The best thing that can possibly be done is to say, when I get breached, I need my infrastructure to still be stable. So I want to always be able to trust my infrastructure. Even if I can't trust my application and I can't trust the data that is originated from that application, I still need to be able to trust the infrastructure, right? Because I need to be able to take machines offline. I need to be able to reprovision them. I need to be able to, roll back and hot deploy software in a trusted way. If I don't have a trusted rollback mechanism, what good is that going to do? I'm simply going to roll back into another piece of software that I don't even potentially own, right? So the bottom line is, I need to trust my infrastructure even if I can't trust my applications. And so that's where a SmartNIC comes in. So basically, when you hear SmartNIC, and you can even look it up, it'll include everything from like a 10 gigabit adapter with some offloads. Like it might have enough smarts to do some TCP handling, or it might accelerate some crypto functions or something. Those are dumb NICs. Those aren't SmartNICs. All that's doing is making it so the host runs a little bit better, which means it's only solving that first problem, that compute problem. It's not solving the attack surface problem. So for the purpose of this presentation, I'm going to say that a SmartNIC is just a computer. Okay. It can be treated like an entire computer. It's got a memory subsystem. It has some amount of compute power where you can run applications. It's got, we can just assume it's Linux. It's got some kind of embedded Linux. But the point is, it's deployed on a network adapter. So the reason for this is a few things. One, we know that applications are moving closer to the data. The edge is becoming where everything is done, and the pipe is becoming just sort of a big, fast, dumb pipe. So if we want an isolated environment in which we can run some kind of security control, the best place we could possibly do it is something hanging off the host, which is not on the host, right? We know the host is a target. If we can get it to be as close to the host as possible and have some effect over the host, but not be there and also not be on the infrastructure, that's going to be the most scalable, but still the most relevant thing we can do. Especially since the data that we're operating over could even be terminated on the NIC, where we still have access to raw data and we can still implement our security controls. So this is sort of what we came into. We figured out that if we could put security controls in a programmable way using regular compute software, throw it on a network card, have the network card hang off the PCIe so it's still connected to the host. That's sort of the ideal situation, but I'm gonna attach some caveats here. Excuse me. So these are sort of my must-haves for classifying a SmartNIC. Some of these will be obvious. So obviously we want some kind of high-speed networking. I'm mostly talking about 25 gigabit and upward. The reasoning here is that we're talking about data center hosts that have you know, let's say 48 cores, 64 cores, a large number of cores on board. It'll have a large number of memory, you know, 1 terabyte is not uncommon. We're protecting services that are deployed at scale. And if you multiply out the bandwidth requirements by the number of VMs or containers that are running on the bare metal, and you want to still secure that network traffic, it needs to be high performant enough. The next is some set of offloads that you would probably find on a dumb NIC. But these are things like crypto offloads or things that you don't want done on the host. The networking virtualization I'll talk about in a second. If you're not familiar with how NFV works, we'll go into that with a few examples. I put security and trust bonuses because, well, the security software is more or less the same. It's just kind of done in isolation. But the idea is that within this sandbox here, it needs to be like a plus, right? It can't be exactly what's done on the host, but done in the NIC. It has to have some additive value. So the software flexibility is there because we have to be able to deploy and manage it like an appliance or like any other piece of software that we would deploy, like an agent or something like that. And it has to be managed as if it were a deployed node. So for example, if I want to deploy new networking policy or new authentication policy or something like that, it has to be able to tie into the normal DevOps cycle that you would normally be using. So if you're running, say, Ansible to make sure that all of the authentication policies on all the machines in a data center are in sync with each other and up to date with whatever authentication policy you've got version controlled, we want to treat the SmartNIC as the same exact thing. So treat it like a deployed endpoint. So let's take a look at what a typical SmartNIC will look like. So there's a lot of junk here, but it's actually not a lot. I'm going to try and go through it a little bit here. So first off, since the NIC is just a networking card with a computer on board, we have to have some measure of assurance that the computer on board the SmartNIC came up in a trusted, known way. So normally this would be done with something like registers that indicate the state of the world so that you can check them against a gold state, for example. It could be that you're verifying the signature on some early boot image or possibly even the firmware itself, and you do that verification in hardware before you boot the system. Either way, we need this to be a trusted compute entity on the network. So we don't even want to attach it to the host until it's booted up in a good state, okay? And by doing that, that means the host will actually be completely disconnected until we verified the authenticity of the security controls on the SmartNIC, right? Because the host can't do anything without a NIC, right? Next up is we've got some kind of policy. These are just a couple little examples. But the idea is that security policy is defined elsewhere. It's usually version controlled. It's usually tied to the applications and the configuration themselves. So if you can imagine in your head when you're deploying software, let's say you've got some kind of security policy in like a distributed key store, like etcd or something like that. You would typically have these type of rules, right? They may not be flow rules because these are kind of NIC specific, but you could have things like application controls and then what actions to take on violations, things like that. Those would normally be revision controlled network security policy, right? And then we'll have some number of accelerators. So these are kind of the typical accelerators that you would find in a modern day high-speed network card. So these are things like packet classification, packet header parsing, some offloads to do bulk crypto. So for example, excuse me, if you're doing TLS on the host, ordinarily you wouldn't actually do it in software. You'd have some offload engines so that it could be done efficiently. Those are still going to be present. We're going to make the case that these will also be used by the embedded compute to do some neat things. I'll show you that in a little bit. And then we've got some type of compute hanging off here. So I just threw up 16 cores connected on some memory subsystem. You can think of these as normal cores. They might have like shared L2 between a couple of cores with local cache, and then they might be distributed to a larger, you know, say DDR4 channel or something like that. It's a computer, right? With a normal memory hierarchy. Okay, and then there's two important pieces here. The first is that I'm going to claim that a SmartNIC needs to have two dedicated types of interfaces. So the first one is going to be a data link, and this is where virtual machines and containers and anything running on the host gets all of its data. This is the high-speed data link that you would normally connect through some kind of external switch. And then it's going to have a management link, okay? And this is where you would get something like, if you're going to control the NIC or reconfigure the policy or maybe modify the security controls that you want to apply to the host, it would be done through this management NIC. So this isn't kind of a new concept if you've deployed appliances before in a data center. They're always separated like this. But the idea here is we want physical separation. So if you imagine like a concrete wall between these two, we don't want data packets to be interfering with anything listening for management packets and vice versa. Okay, so the last thing is all of this is connected via PCIe to the host. And what that does is the host NIC will look like a NIC to the host. The host will see it as a high-performance network card. Underneath the hood, what we've done is created an isolated sandbox where we can run our security controls on behalf of the host. The host doesn't even need to know about it. And we have a place where even if the host is breached, we've got this sandboxed environment where we can do things like take it off the network, we can raise alerts, we can modify ingress and egress traffic at will. We can even run like a full Nginx on this, terminate all traffic, and then put all of our controls right on the NIC. So let's go through a few of these. This is how we create isolation. So normally, if you think of a PCIe card like a GPU or something like that, it's actually not that isolated. The host uses it for anything it wants to do. And this is pretty true for most PCIe cards. Because of how the PCIe is divided amongst the different resources. What we've done here is kind of the most basic thing is we said, look, we want the host to still be able to create VFs and PFs on the device. These are physical functions and virtual functions. In this case, there's always a physical function which you use to allocate stuff on the NIC. And then you can create any number of virtual functions, which means you carve up the PCIe bandwidth to use as you will. We still want the host to do that. But instead, since we've got a little embedded computer here, the normal physical function is a fake physical function, okay? We create a virtual one on our side, so we still want the host to be able to do its stuff, but we don't want it to be able to do anything under the sun. So it can configure it how it wants, and we've got a parent physical function which is connected directly to the embedded compute. So we can override those commands if it wants to do something that's against policy, for example, like create a VF to a container that we haven't authorized. We can make sure it doesn't happen. We can also make it so that the actual switching behavior is not controlled by the host. It controls its little subset, but the host isn't controlling any of that. The host is simply controlling its own portion, and the NIC itself is in charge of the main portion. And I'll get into each of these components a bit more, but the important part is we have to have an embedded switch to route packets. We have to have some type of embedded compute to make sure that this is in policy and to make sure that this isn't misbehaving, right? So the second part of isolation. What you normally do is something called SRIOV. That's basically a way to make sure that you can run at near native speed, even when virtualized, okay? So if we take a look at each of the VMs, what you would normally do is you would have a para-virtualized NIC driver within the hypervisor, and that's kind of emulating a network card. And then the hypervisor would be in charge of taking the packet from the para-virtualized NIC and giving it over to the actual NIC, right? And that's all done in software. With SRIOV, we allow the VMs to actually communicate with the hardware. And so it bypasses all of this and gives them their own little slice of the PCIe bandwidth. So what that does is it means that this traffic is actually physically isolated from this traffic. They're connecting directly to the PCIe, and they're not commingling with each other, and they're not interfering within the hypervisor. So that's isolation step number 2. So let's take a look and kind of piece out exactly how these are accomplished here. So across the gold fingers on the actual card, we've got virtual functions that are kind of cohabitating the physical hardware resources. With SRIOV, there's no hypervisor involvement or there's no hypervisor interaction with any of the packets that are going from the VM to the NIC. We've got basically bare metal performance. We've got this fake sort of physical function that the host sees. It still thinks it's in control of the NIC, but actually the embedded compute is in charge of the NIC. And then we've got this sort of override behavior in the compute. And so here's how we would normally program the embedded switch, or really any network type of packet processing pipeline. I don't want to spend too much time on this, but the idea is, if you can imagine cobbling together any of these triggers, like say, could be on a 5-tuple or a destination MAC, or it could even be a session or something like that. I'm going to match on that. I want to take some action. The action could be manipulate the packet. It could be drop the packet. It could be simply move it to VM number 1, because that's where it should be destined. And then it's got some logging or cataloging capability, like incrementing a type of counter, and then a next pointer. So think of it like a tree of actions you can take, and there's a deterministic set of actions for every incoming packet. That's the way switches normally work, right? So the way this works in a SmartNIC, and again, I'm going to use Open vSwitch as sort of the standard here. If you're familiar with the XACML policy model, it's maybe a bit old school, but the principle still applies. What we've effectively done is turned this portion of the SmartNIC into the enforcement point for that policy. We've turned the embedded compute into an additional enforcement policy, so we can enforce policy in software. We can also make decisions about policy, again, on the software embedded in the NIC. And then we can create any number of additional enforcements on things like, well, host for one, I'll show you that in a bit. We can also do things like, is one VF using too much bandwidth? Is it connecting or accepting connections from things it shouldn't? That kind of thing. Okay, so the way this normally works is, if you're familiar with vSwitch, this will be a repeat. If not, what will happen is, in order for this to perform at native speeds, we'll have a packet that comes in. It'll miss in the embedded switch. It'll go all the way to the embedded software, where we'll look it up in the policy, and we'll say, yeah, this packet is within policy, or no, this packet violates a security policy. This will make that decision and then program it into the embedded switch so that subsequent packets are at near native speed. They're completely offloaded. And again, that's just to solve the compute problem. It's not actually addressing the attack surface problem. So let's look at that. This is a made-up policy that I created. So I'm gonna say here that there's 2 hosts, this one and this one. It's not always done this way, but often you'll find that containers are deployed inside VMs. It is becoming a little bit more common to do bare metal containers, but not really. Most of the time you'll still find containers inside a virtualized environment inside a host, which is a little funky, but that's just sort of the trend. So I've partitioned these into what I'm going to call different tenants. Think of each color as a different tenant, and this would be, if you're not having some kind of commingled multi-tenancy software solution, this might be like a container or a set of containers per tenant. I've connected them through some kind of combination of SRIOV and VFs that are allocated on the gold fingers, so that each of these hosts have networking bandwidth from the PCIe. And let's just say that I want a policy up there. I want to say tenant 1, database 1 can only talk to HR processes. Okay. Now this is a completely made up policy, but this is one that is typically implemented around firewalls or microsegmentation or least privilege type network access, right? So let's say that this application needs to make a database request. The way this is normally done, after it resolves the address and all of that, it'll initiate a networking handshake, and it'll find its way across the network, spanning through the blue path, which is the data path, get routed back here, and then into database 1. But what if I want to make that path a little bit more robust and say it can only talk to it? I can do that through a few things. I can create access control lists and put them into a firewall. I can do things like the above and say, okay, I want a custom encrypted tunnel between this tenant and this tenant, so that even if there's a rogue tenant and it clips on in some way or starts intercepting traffic off the hypervisor, that it still can't do anything with it. This is a custom per session encrypted tunnel. So how would we actually implement this? First of all, I dig this type of use case because it's sort of typical of a multi-tenant environment. Most of the multi-tenant breaches you see affect all customers, right? They typically don't have any kind of per tenant or per application isolation, but I'm assuming that that's the policy they want. Let's see how we can possibly implement that. So this would be the checklist, right? So the first thing I'd want to do is authenticate that it's a legitimate policy, right? That's usually done on the management layer. Then I'll program some set of flow tables. It could be in the NIC or it could be in the agent or something. But what it'll typically do is say that a certain packet from a certain destination is going towards a certain host, and that'll have a flow associated with it, right? I'm going to have to exchange some information between these two because there's going to have to be an IC, right? There'll have to be some kind of key exchange before we can create that tunnel. Then I'm going to have to figure out, okay, the policy says I've got tenant 1, database 1, and tenant 1, HR 1. Where are those actually located? So I'll have to figure out on which host they're running and then which SNIC is associated with those hosts. Create the tunnels and then track it. This is a bit complicated, but this is sort of the checklist. We'll go over how to actually implement it in a second. These are the steps that need to be taken, okay? The problem is these need to be programmable enough to accept policy like that. So in order to do that, I'm going to say that SmartNICs have a number of options. And if you look at SmartNICs on the market right now, these are the typical options, okay? So we'll have things like the exact same software you would have with a virtualized network function, but shrunk down and running on the NIC. That's option number one. It may be kind of crappy, but at least it's an option. The next one is manipulating traffic within OVS. So this is actually a pretty easy one. I'll show you an example. If you've got, has anyone heard of DPDK, the Data Plane Development Toolkit? It's developed by Intel. And now it's open source. It's developed by a huge community of networking companies. And what they're essentially doing is giving you raw access to all of the networking interfaces, and they provide a nice library for doing that. So I can grab a raw packet from interface 1, do something with it, put it onto raw interface number 2. The next is to take a pre-built, sort of like a security appliance, like an Nginx or an HA proxy or something, and actually run it directly on the embedded compute within the SmartNIC. I can also just simply do it in Linux, right? I can utilize NetFilter or the transform module to create any of those IPsec tunnels I just talked about and just do it right within the networking kernel. And then lastly, just make it up. It could be anything at all because a SmartNIC is a computer. It's got an embedded Linux, it's got embedded memory, it's got access to all the same devices and resources that the host does. It's just embedded and isolated. So let's take a look at how to actually do this. Let's say I want to do the OVS model, okay? Within Open vSwitch, if I create a single switch within OVS, and let's say I give it, here I'm using ENP as the various types of data ports. I'll add those to the vSwitch. Representer 0 here is a NetDev representer that would represent the link between the NIC and the host. I'll add that to the switch as well. And then what we have is a software model for how packets would flow from the wire to the NIC to the host. So let's just start adding some rules. So this is just a quick set of rules to do connection tracking within Open vSwitch. So we'll do things like say, ARP traffic is okay. Down below, DNS traffic, that's also okay. If we get anything else and it's an IP packet, doesn't matter what the layer above it is, but if it's an IP packet and it's not being tracked, the -TRK, let's add it to the connection tracking table. And then if we've got a established and tracked packet, let that one through. this is a very typical type firewall policy. It's basically just saying everything is good, and I can restrict it more after that. So what would it look like if we tried to restrict it a little bit? So here we want to say, well, let's say we want to allow inbound SSH, right? So if we've got a packet coming from the wire, and it's a TCP packet, and the destination is 22, we can add it to the connection tracking table, and we know that downstream, the switch will allow it into the host. If we wanted to do the same for outbound traffic, these are some example rules. But the idea here is, this is all implemented and enforced on the NIC. The host has no idea this is going on. So normally what would happen is the host has its own set of IP tables or firewall on board. It might be a virtualized firewall. If the host is ever compromised, the first thing that's going to be manipulated is the way to get traffic into the host, okay? So what we've done is we've taken the first line of defense, which is usually a security group or a firewall or something like that, and we've offloaded it onto the NIC so that it's no longer on the same trust domain as the host. And that way what we've done is essentially said the host can have its own more finer grained policy if it wants, but we've still got an isolated, separately managed way to control network ingress and egress. Okay, so that's sort of one example. But we can get a lot more complicated than that. We can actually embed basically anything. So what I'm going to say is, if we've got this embedded switch and we've got some kind of compute, we can hang anything off of it, right? So let's say what I wanted to do is have a man in the middle running in the NIC to intercept traffic and shape it. It could be for something like, you know, metering my tenants or services, or it could be enforcing some networking policy. But I can actually approach it the same way. All I need to do is create a VETH pair, hang it off the embedded switch, attach one end of the VETH pair to the application that I want to have added into the switch. The other end goes into OVS, and I can create the same type of rules. I can say anything coming from the wire needs to go to the VETH tail for that isolated app, and then the app can communicate with OVS, and then that goes to the host. So I can interject anything I want to do. So you would see, if I wanted to do this in OVS, all I did was I created a VETH pair and then added it into the switch, and I can dangle whatever application I want off of that through a tap interface or literally anything. So let's go back to the policy that we made up and see how we might implement this. So assume we want to do it in OVS. We take the same steps that we followed before. We would create an OVS instance, configure it as a switch within the embedded compute inside the SmartNIC. We'll create some kind of VETH pair and connect it to the switch. The VETH tail would go into the Linux kernel. We're going to modify the Linux kernel to do what you would normally do in the transform module, which is create a security association. It'll have a session key, which specifies the type of encryption to apply. We bind that against the other part of the security association, which is the match criteria. And then as long as we forward packets into the Linux kernel, if it matches that criteria, it'll get encrypted the way we want it to. And then on the opposite side of the OVS switch, we can dump it out onto the wire. So the host will never know it's happening. This HR app will want to communicate with the database and will let it. But inside the SmartNIC, we'll be intercepting it, wrapping it in a custom encryption protocol, and sending it off onto the wire. So this is how we would take a very straightforward policy like these two can only communicate with each other, and we would remove it from the host so that the host has no idea that it's going on. We would put it in an isolated environment where the only way to modify it is to go in through an out-of-band air-gapped port, okay? And then it would act on behalf of the host. It's still connected to it, so it's still very close to the data. So anything coming out of the host, if you clipped into the wire, it would look like normal host traffic, except it's totally encrypted, right? But it's actually not quite perfect. So what we're doing here is we're saying, okay, we want HR apps to talk to databases. And we're doing that by identifying the networking criteria for this HR app. Like we might know its IP address, for example. We'll say anything from this IP address to this IP address needs to be encrypted by criteria X. But that's a bit weak, right? So it would be much more robust if we actually knew that it was the real application and not just a 5-tuple that's associated with that HR app. And it would be great if we actually knew the runtime criteria of this. So we could say something like, an HR app with a valid signature can only talk to database 1. That would be a very powerful statement. But we can't do that with this alone. So what you can actually do with a SmartNIC is make this a little bit better. So I'm gonna pose a few questions. What if we had some more information about the host? For example, since a SmartNIC is a PCIe device, it can access all of host memory, right? And literally all of it, I mean all of it. And this might ring some alarm bells, but hang on for a second, and I'll show you why that's okay. But the idea is PCIe devices can already access either selected memory based on configuration, all memory based on configuration, and it can access it very, very quickly, right? It can access it for Gen 3, it's about 1 gigabit per second per lane, and there might be up to, say, 16 lanes on the PCIe bus for a given device. So here we're talking about 16 gigabit a second reading host memory, just looking for stuff. Okay, so let's assume that we have that. Next, let's assume if we have access to that memory, we're gonna need an isolated space in which to check it out, to make sure that certain applications are running or not running, what criteria they're running against, like for instance, did they start in a trusted way? Are they authenticated to the network in a good way? Do they match a certain signature, right? So these are all things we wanna ask about that HR app before it can talk to the database. We've also got a lot of accelerators on SmartNICs. So these are specifically for remote DMA. So we can, on a typical SmartNIC, like the one that Mellanox makes, we can take memory from one host and move it to another host at wire speed. So if you're on a 25 gigabit network, we'll be moving memory around at 25 gigabit. On a local environment, like a SmartNIC, where we have 2 hosts dangling off the PCIe, we've got the real host and then the embedded host, right? Those are operating, again, at wire speed, and they're able to transfer memory back and forth. So we've got a very high speed and efficient way to move memory around, right? Okay, so if we put this all together, let's draw another picture. So this is the typical way that systems will be connected to the memory subsystem. If we assume here that we've got some host, I'll label the processor separately here. If we follow the right red arrow, that would be how it communicates with external memory, DRAM, right? If we've got the left red arrow, that's how it communicates over the network, okay? And so it'll follow a path over the PCIe and out through the NIC, okay? So the right, or the left red arrow is already taken care of, right? We showed that we can take a networking function, put it on the embedded compute, and enforce some networking policy. The right red arrow is a little bit funky, but we're a PCIe device, and we're specifically designed to access memory out of band. So if we follow the green arrow, you can see that PCIe devices can access, let's just say read memory. They can read memory in an isolated and out-of-band manner as long as there is available PCIe bandwidth. So without the host even knowing, we can look at memory and make sure it's legitimate, more or less. And more importantly, there's no performance hit. These two systems are designed to be running in parallel. They're designed to be not synchronized, and they're both designed to be incredibly high performance. So let's look at this. So we've got the first part. We've got all of our analysis running in an isolated trust domain. And by the way, I switched from SmartNIC to Bluefield. This is just the name of the SmartNIC that I work on. And the only reason I did that is because doing memory analysis like this, it doesn't work in every SmartNIC. It just works in this one. Okay, so we've got this isolated environment which represents its own trust domain, okay? Next, we've got some accelerators to move memory around quickly, but more importantly, it's a secure memory acquisition because we're running out of band from the CPU, and the CPU can't do anything about it, and it also has no impact on what memory we read. Next, we've got some accelerators to help us out. So scanning memory is tough, especially when you're talking about like a terabyte of memory. So we've got some accelerators to help with that process and make it a little bit more real time. These are things like regular expression processors or checksums, cryptographic checksums to verify signatures, address translation, sticky problems that really benefit from hardware acceleration. Next, if you can imagine trying to take a snapshot of memory constantly to figure out what's going on and make sure that applications are in sync with networking policy, this has to be done incredibly rapidly, but fortunately, the PCIe bandwidth is great, right? So you can imagine, let's say we're interested in a small subsection, maybe a particular VM has a particular kernel table that you're interested in the validity of. It might be in a specific set of pages that we know about. We can hammer those pages constantly on a very rapid interval to make sure that even though we can't have a full trigger, we can have a pretty good idea of what's going on within those tables in the kernel. So that's a real-time type interval. And then finally, we put all these together and we can reconstruct all kinds of memory structures that would normally be in a host system. So you can imagine the process list in Linux, right? The first thing that I would do is I would look up the process information, the task struct for init, and I would walk it and see exactly what processes are available on that system. Eventually, it'll circle back to init, and I have the full picture for everything that's running on that system, including containers operate in the same way, right? Those processes are still within the same Linux kernel. For VMs, it's very similar, except we have one level of indirection past that, right? We have to first find out where the VMs are, figure out what physical memory is mapped to the virtual memory associated with that VM, and then we can walk its process list, right? So we can actually go into memory and reconstruct Linux structures. And I want to show you a demo for how this is done. And this is my caveat. If you're into gaming, especially speed gaming, they have this concept called marathon luck, which means that if you're in a marathon setting, you're guaranteed to bone it a few times. In this particular setting, I've got my hotspot running on my phone. My laptop is on the hotspot, and I have a SmartNIC emulator running on a bare metal machine that I've instanced out of packet.net in the United States. So this is my marathon luck prayer, but I'd like to show you the kind of things that we can do here. And this will be especially fun because I can't see what I'm typing. This is actually, okay, I've got a separate screen down here that I can use. Okay, so I'm gonna log into the machine where I've got the emulator running, and we'll see if I'm still connected to the network. By the way, have you guys used Packet? It's a bare metal yeah, you have. It's awesome, isn't it? We have to use Packet because we're emulating hardware here. If I wanted to run this on a virtual machine, I'd have a virtual machine running a virtual emulator, and inside it a bunch of virtual machines. It would be total chaos. Okay, so this is my instance where I've got the SmartNIC emulator. Oops. Okay, so I'm going to show you a couple of systems here. So in a SmartNIC environment, I've got two systems. I've got a host system and an embedded system. Here, as you can see, this is our host system. It's a regular Linux. I'm not doing anything crazy. But what I do want to do is see if I can analyze the memory associated with this machine on the SmartNIC by going over the PCIe device, capturing a bunch of memory through RDMA, parsing it, seeing what it's doing, and see if I can enforce some policy. So let's start up a process here. I'm going to just ping Google a bunch, and then exit. Now I'm going to go into the embedded compute. Okay, so this is our Bluefield device. If you remember the layout here, I've got a host system. I've got the SmartNIC that's providing it network. and then I've got some embedded compute on the inside. So you'll see, as soon as I want to start analyzing memory, first of all, it's running at emulation speed, but what it is doing is going over the embedded PCIe connection, going into memory where it knows that some structures might exist, and physically walking that memory. So what will exist as virtual addresses on the host side, it's obviously mapped to some physical memory. We have that translation table. We're actually doing the translation in the embedded compute. And every time we want to access some page, we'll do the translation, request the physical page over the PCIe device, get that physical page back and parse it a little bit. So let's say I want to see what processes are running. What this will do is it'll negotiate with the PCIe, simultaneous to doing some network traffic. So we're setting up what's called a queue pair. This is sort of a very primitive type of setup for transferring over RDMA. We're doing some translation, and now we've got the process list for the host. So we're not actually on the host. We're on the NIC, but we can see exactly what's running on the host. I mean, timestamps aside. Okay, so let's scroll up here and see if we could find our process here. We've got some drivers. Oh, there we go. I could see ping is running. I could see if, obviously the timestamp is not correct, but it's ahead of the system boot time. And I can see it's running in user space. I can also see the exact state of the rest of the drivers that are running, as well as any watchdogs or daemons. Now let's say I wanted to, remember, we're trying to implement this policy of a certain application can talk to a certain application. So let's check out what applications have open network sockets. This is a table that's maintained in the Linux kernel on the host. So we're going to go across the PCIe bus. We're going to access a bunch of physical memory. We know where the kernel structure starts. We're going to parse it out, doing the translation from virtual to physical. And once we reconstitute it, we'll be able to see exactly which processes have a network socket open. This is where marathon luck comes in. Okay, so again, this is a normal Linux kernel structure, so I can reconstitute it. I can introspect into the host and see what's running. If I look around here, you can see what ports are open. You can see I'm listening on this SSH port. I can see a full snapshot of every application that has network activity going on. And so if we go back to the policy that I was trying to create, what I really wanted to do was say HR app is the only one who can talk to the database. And previously I had to do it based on IP addresses and networking stuff. Here, I can actually go into the machine, I can find that HR app, and I could see, okay, it has a network socket open. I can figure out its PID, its process ID, verify that that process is in a good state. I can dump the entire process, look at it, verify the signature. I could say, okay, not only is this thing in a known state, I recognize the signature, but yes, it's allowed to attach to the network. I have the network connection parameters, like, for example, I know exactly which port is associated with that HR process, and then I can apply my encrypted tunnel. And I can do the same on the database side, too. Finally, you can see I was playing a bit. Let me show you something really cool, actually. So we connected to this framework. Are you guys familiar with the recall memory forensics framework? Anybody? Awesome. So normally what you do with toolkits like that, same for things like volatility or any post-mortem forensics library, is you'll take a crash dump or a memory dump from a system that you want to look at. You'll take that entire file, feed it into the forensics library, and you can dissect it a little bit, right? Well, we've done something very cool where we took the same concept, except where normally something like recall would be operating over a memory dump. We manipulated it so that anytime I want to access a page within that memory dump, it's going to go into the host and do it live. So instead of operating over a static dump, we're going to operate over live memory instead. And there's a million plugins for recall. I'm not going to go through them, but I can do everything from dump a process to you can see I was playing with dumps. These are all process dumps. So earlier I did an entire dump of the machine, took every process, dumped it into a file so we could check it out. These are things that I can do live on the SmartNIC to make sure that the host is behaving properly, right? So whether it's a VM or a container or just applications running on the host, the SmartNIC is this isolated, sandboxed environment where I could reach into the host, manipulate or not manipulate, but pull out the memory and manipulate the policy associated with anything that's running on the host. So it's kind of a novel way to make sure that, one, the host is in compliance, two, that it's accessing the network correctly, three, that I'm applying network policy based on the criteria of the host and not just guesses for what it might be doing, and four, just making sure that the host is in a good state with regards to the processes themselves. I only want to be running processes I know about. I don't want to be running anything else. So in my NIC, if I go into the system and see that there are 20 processes and I have no idea what that 20th is, it doesn't match any signatures, I know it's not on my whitelist, and I can just disconnect that host from the network right away, right? I just deal with it later. It might be legitimate, and I might have forgotten about it. It might be part of some new rollout. It might be illegitimate, and it might be part of some breach. But either way, without having to worry about the infrastructure being affected, I can modify the host's relationship to the infrastructure from the NIC. Okay, so it is almost exactly noon. That's what I wanted to show you, is to show you how SmartNICs can change the way we think about host security, and basically to merge the idea that networking security as it gets closer to the edge or closer to the host doesn't have to be on the same trust domain as the rest of the host processes. And then the memory analysis is something that we're working on, which we think is quite promising, if not a little bit scary at the same time. Do you guys have any questions for me? Yeah.
We got a microphone, hold on.
Ah, we have a mic, all right.
Not you.
First of all, great talk.
Thank you.
Quick question. So you're dumping the memory from host. Can you write back to it?
I don't think we want to go there. So
I do.
I know. So here's the thing, right? We're trying to be side effect free, and you don't know exactly what's going on the host. And I'll give you a perfect example. Okay, so something like the process list, right? It's a linked list, okay? And that means that we are bounded in validity by the total time it takes to make one transaction, parse it, and then move to the next transaction. So let's say I have 100 processes. They're going to be in a list. I'll probably have one page that represents one task struct from the root. I need to fetch that, check it out, grab the next pointer, fetch that, check it out, grab the next pointer. So in a read operation, that might not even be safe, because the task list might change in the time it takes to actually parse and understand what processes are running. The best we can do is make an educated guess. We can probably, with some degree of certainty, figure out at a given instance that a process node that we found is legitimate, because they're all sorts of other indicators. I can see the liveness state of that particular task. Memory associated with that task would probably not be valid if I wanted to check and see if that task has died and its place subsumed within the process list. So even the task of reading what's going on the host is not exactly side effect free. There's an inherent race condition that we're trying to overcome through performance on the bandwidth side. Writing would, I would say, be even more catastrophic than that. Yeah. You have a follow-up?
Yeah, follow-up. So you can write it, you don't want to.
Yes, correct.
Okay.
And in fact, I mean, they do write it. Like PCIe devices do write to memory. It's just normally they're granted supervised privileges by the host. So it'll say, I've allocated this buffer. I know it's going to be written, so it's volatile memory.
Hi. You mentioned obviously on startup it's got to do a firmware check to make sure we're in a known good state before initialization. given that I've had plenty of dumb NICs fail in their time, I'm obviously highly, worrisome about single point of failure. How mature are we looking at in terms of slaving multiple of these units together to get some level of resiliency in terms of management tools? Because if we're going to have to patch down the line, because again, it is just another form of Linux somewhere down the line.
Yeah, no, yeah, exactly.
Where is the market in terms of that? Because if I'm in a position where we are pushing some of our stuff to cloud and some of our stuff database refresh, so we are looking at architecture stuff. I haven't looked at this prior, so how mature are the management side of things for actually keeping these devices
very
stable?
immature, very immature. So for example, I'll give you an example. If you're on Azure, they use SmartNICs. They advertise it quite readily. Theirs are based on FPGAs, so that's what they use for the embedded compute. I talked to one of the developers at a conference lately. I think it was maybe 2 months ago, and I asked him that exact same question. He said if there's a mismatch on the bring up or something goes wrong, or even if they need to redeploy based on a firmware change, they take that node down for anywhere between 2 and 5 hours. And it's simply because of that problem. They have to verify the known good state, and there isn't a good way to do it. So the answer is to be redundant. That's the only thing we can do. It's much easier with a software-based model than an FPGA model, but you're still going to have to rely on redundancy.
Any more? Then me. When I look at everything you've just said, which all sounds relatively awesome in terms of capabilities and so on, I see a huge, massive complexity when most of the admins I deal with in my day-to-day supervision and so on are having problems managing the Windows GUI, let alone Windows Core, let alone configuring a SmartNIC on a Linux host to correctly read, talk, process, etc.
I agree.
How do you resolve those two in your opinion, or where are we going with that?
Yeah, so that's why if you look at the deck, let me flip back here. Basically, what it comes down to is our position on that is that we're trying to create. Oh, I don't know where the slide is. We're trying. Oh, it wasn't showing anyway. We're trying to create the right tool set so that vendors can create the right solution. So I would say that SmartNICs are more on the technology side. They're not meant to be exposed to someone like an IT admin, because you're right, it is far too complex, and it would actually increase the attack surface rather than decrease it. Rather, I think the right position is to treat it sort of like secure enclaves from Intel, where you have this great tool. Well, if we go back a year, it was a great tool to create the same type of privileged execution environment. But you know who used enclaves? It wasn't normal developers. It was people like Visa. So they would develop a solution which runs on your host, which creates an enclave so they can do their trusted compute there, and they don't have to do it in an unsandboxed environment like a browser window. So I would say that this type of technology is best suited for vendors like that who would create their own policy engines that you can use more like a Windows GUI, and you shouldn't be mucking about with memory unless you're someone like that.
Then my follow-up is, what do the major cloud providers feel about this aspect of the tech?
Yeah, so interesting choice of words, the attack there. So there's really two types of deployments that you'll see with SmartNICs. The first is the large hyperscalers, and typically what they would do is they want to be in a position to create security add-ons for their customers. So for AWS, for example, you can't create an instance without specifying a security group, right? Now that security group is not implemented on the host, right? You're not going to spin up a host and see a bunch of IP tables rules that represent your security group. Instead, it's implemented on some machine just next to the VM, probably right in front of it, okay? And AWS is actually in the process of making that more SmartNIC-y, okay? So their rollout is that the hyperscalers see it as a trusted way where they can control policy on behalf of their customers, okay? So when they define a policy, they don't want to interfere on anything you're doing in the VM, you own that, but they still want to provide some measure of security for you to take advantage of, even if you don't know how it's implemented. And that would typically be done in something like a SmartNIC. I would propose. The second one is more like an enterprise data center. So if a company owns the entire rollout, like say it's a colo and they're racking and stacking, they therefore control the NICs as well. If they used a SmartNIC in that capacity, they own the host and they own a NIC, and they're in sort of a symbiotic relationship. So for example, if you were to take Nginx and deploy it on the SmartNIC, you would control the session keys there. You would also control the session keys on the host, and you can make sure that normally you can't intercept TLS. You have to terminate it in some kind of knowing way, and you have to make sure that the host trusts the CA that's associated with the SmartNIC. So in that case, they both know about each other. It's not like the hyperscaler where they only control this one and the customer controls this one. In an enterprise, they would know each other, and they would just be using SmartNICs to create a better security posture. Those are the two types of rollouts.
Thank you. Any more? Thank you very much. And,
yeah, absolutely.
I will also say I'm always scared when I hear deploy Nginx on my NIC.
Yeah.
I understand what you mean, though.
No, it's totally funky. I've done it. It's very cool. It's incredibly satisfying. So, it's just one of those funky things. If you have any questions, by the way, I'm not much of a Twitter person. I have a Twitter account, but it's mostly used by a bot to post World of Warcraft live status updates. It's not actually used for actual information. But you can email me. It's Jack at the company name Mellanox. I'm the only Jack in the company. It's one of the advantages of working for an Israeli company.
Thank you very much, everyone. I believe lunch is being served shortly, if not now.
12:07 lunch.
Excellent.
All right.
That will be on the first floor when it happens, and see you again this afternoon.
I just want to give a shout out to the AV crew. They were working up until like 60 seconds before the talk to make sure everything was awesome. So those guys rock.